Okay, so electricity, we're going to start. It starts with current. I think most of this you would already know from GCSE. So current is basically uh, charge per time. So the flow of charge, basically, rate of flow of charge. That's current. The formula is very simple. I equals delta Q or delta T. I'm just going to write down the formulas here. I should have moved the pen. Let me just do that quickly. All right, done. Okay, good. Okay, so the first formula, I'm just going to write it here. These are the basic ones that you should know. So I equals delta Q, change in charge over change in time. So that's the first formula. And just to give a definition of unit charge, they've written 1 coulomb because that's the unit for charge. So 1 coulomb is defined as the amount of charge that passes in 1 second when the current is 1 ampere. So obviously, when you put everything equal to one, you'll get the definition. So that's fine. The smallest charge that is possible is of an electron, which is 1.6 times 10 to the power minus 19 coulombs. It is denoted by a small e. So whenever you see a small e, that is the charge of an electron. We're just going to use that as our basis, and that is the possible uh, smallest charge that we have in all of the questions and everywhere around us. So that's that. The other thing is potential difference. So we have multiple formulas for potential difference, but when we come to the definition of potential difference, that is in terms of the work done. So potential difference is basically the work done per unit charge, which also gives you the formula for it. So potential difference is the work done on a unit charge, whatever is the unit charge, which is per coulomb. Per coulomb basically. So it's V equals W over Q. So that's also basic. I think we know it from GCSE as well. So work done per unit charge. That's the formula. All right. And then they go for the definition as well. If you put one for all of them, what is potential difference? So that's 1 volt if you have 1 joule of work done on 1 coulomb of charge. So that defines 1 volt of potential difference because that's the unit we are going to use for potential difference. That's that. Uh, Work done on a charge equals the kinetic energy it gains. So it can also be written in terms of kinetic energy. So uh, work done on a charge is equal to kinetic energy it gains. So because we want the work to be on one side, so basically we have to move Q on the other side. So work done would be equal to VQ. And if we have it written as VQ for an electron, we can write it as E instead of Q and V with that. And that should be equal to kinetic energy. So work done is also equal to the kinetic energy. If I just write it like this, work done is equal to kinetic energy, which is half uh, mv squared. That's the basic formula for work done. And obviously, you know that you can replace W by VQ, and in terms of a unit charge, which is equal to an electron, you can replace Q by E. So W can be equal to EV in that case if you replace Q by E. All right. So that's that. Then we have mean drift velocity. Now, because uh, charge flows because of electron, that is the convention that we are taking. So the convention used to be that it is the positive charge that flows. It used to be in that way, but now scientists know that it's basically the electron that is flowing. So uh, we take E everywhere, like you've seen. So mean drift velocity is obviously the electron is the thing that is flowing when there is some current. So the electrons, they have like random motion. It's not like they are always moving in, like they're going in the same direction every time. They don't move in a straight path like that, like going through the flow of your, but their mean velocity, like eventually they are going to move in the direction of the current. So mean drift velocity actually caters that. So we know that electrons are going to move from the positive potential of the cell or a battery, and then they go towards the, sorry, it's opposite from negative to the positive. We are considering electrons. This is the new convention. So mean drift velocity would be the average velocity through which the charge move. Obviously it has random motion as well, we don't count that. In case of mean drift velocity, it's just the flow that it takes. What's the direct path, because that is going to be the velocity, because velocity is displacement over time. So eventually if it reaches the other end of or other terminal of the battery, that is what we are going to take. So that is mean drift velocity. The definition here is the mean drift velocity is the average velocity of the charge carrier. So average velocity, because it has random motion as well in other directions other than the flow of current, but we don't count that. We're just going to count for the mean drift velocity. We're just going to count the, we're just going to assume that it goes straight from one terminal of the battery to the other. So that is mean drift velocity. The mean drift velocity is the average velocity of the charge carriers. So the formula for that is I equals A N EV. So I'm just going to write that here as well. So that's the flow of current that it's representing, EV. Now in this case, um, A is the cross section. So whatever is the, what kind of wire you're using, what is the cross sectional area of that. So that is represented by A. N is the number density of the electron. So number density is the number per unit volume. So whatever is the number of electrons that you have in a unit volume, that is represented by N. Obviously, for a metal, this would be a greater number, and for an insulator, it can be a little bit up from zero. And if some metal is a better conductor than the other, obviously the N would be greater for that. So it depends on, totally depends on the material that you are using as a medium for the charge to flow. So N depends on that. It's called number density. Its unit is per meter cube. So the number of electrons per meter cube is number density. E again is the charge of each electron, which is 1.6 times 10 to the power minus 19 coulomb. V is the mean drift velocity. So whatever is the mean velocity, like how it goes through the circuit. So that's the mean drift velocity. Obviously, we're not considering the random motion of electrons in this case. It's just the mean drift, how long it takes for it to start from one terminal to the other. Then you measure the distance of that, and then you divide that by the time it takes. So that actually gives you the mean drift velocity. So it does not consider the random motion at all. Different materials have different number of charge carriers. So again, as I told you, N would be different for different materials. For a very good conductor, obviously the value of N would be greater than something like an insulator, which for which it would be very, very small. So if you want more current to flow through something, you have to look at N for that. What is the value for N? It's different for different materials. Uh, Charge carriers in liquids and gases are ions. So obviously, in case of metals, it's usually the electrons that are the charge carriers. In case of other things like ionic compounds, for example, it's the so it's basically the ions that actually carry the charge. The positive charges flow from one point to the other, and the negative flow from the other point to the other. So it's basically that. And they say that, so you already know, I think it's in GCSE chemistry that we know uh, basically that uh, ionic compounds, for example, they don't conduct electricity like that. So if you have table salt, obviously it won't conduct any electricity like that. Either it should be molten, so in molten form they are in the form of charges, or they can be in an electrolyte, because these are the only two ways you can split them into positive and negative charges. So that is what it says here. So that is the only important bit that is in this. Then we have resistance. Every material has a resistance. Obviously, even metals have some resistance. Some would have more, some would have less. Obviously, insulators have the highest resistance, so they don't like the charges to flow through them. So that's that. And for that, this is the most general formula that you use. R is equal to V over I. I write it as, I'm just going to write it here. So V equals IR. So that's one of the other formulas. Uh, so that's that. So this is written here. You know what is R. R is the resistance. It now R depends on different things. It's not that you just take gold, for example, and the R would be fixed. It depends on its geometry. It depends on the temperature. It depends on a lot of stuff. So, but generally the formula is R equals V over I. So that's that. Three things. Yeah. So that's how it says here. So what is the resistance dependent on? So they have, I don't know if they have not written it here, but you will see it later. It depends on the temperature as well. So resistance changes. Usually, for in most of the cases, the resistance is less when something has more temperature compared to when it has less temperature. So that's that. But the formula that we usually use is R equals rho L over A. So I'm just going to first write it here. So R equals rho L over A. Now, this is what resistance depends on usually. So, rho is basically not density in this case, rho is resistivity, L is the length of that material, whatever the length is. A is the cross-sectional area of that. So now it tells me that if the length is greater, obviously the resistance will be greater. If you have like if you use a longer cable for to charge your phone. Now I'm not completely sure. I know in the case of a charger, it like adjusts it because it has to give the same value as an output. But if you increase the length of that, it should and you keep the voltage fixed, it should change the resistance of that, which means that obviously how much potential difference it needs. Uh, Cross-sectional area, if you have a like a bigger diameter cable, it will have less resistance. Now, resistivity is something that is related to a material. Gold would have some resistivity value at a certain temperature. Similarly, all other metals, all other insulators would have a resistivity value. So it depends on the material that you are using. Obviously, this resistivity has some dependence on the temperature as well. So this changes when temperature changes, and that's why resistance changes for the same material as well. So because it is dependent on temperature. For some things, the dependence on the temperature is not that much. For other things, you have more dependence on the on temperature, which those things we call as thermistors. We can use them to control how much current flows through them at different temperatures. So that's that. Uh, yeah, so what does it this say? For an ohmic conductor, R is a constant. So obviously, for an ohmic conductor, the relation between potential difference and current remains constant. It's a straight line. So as potential difference increases, current increases as well. There is no and we say these kind of conductors are ohmic conductors because they obey V equals IR. So anything that obeys V equals IR, we say that that is an ohmic conductor. The non-ohmic conductors, they don't uh, actually obey the Ohm's law. So basically, V equals IR does not totally reflect how they work. So whenever you see a straight line, you know that this is an ohmic conductor. All of these equations we talked about, they hold for that. So that's that. And V equals IR basically is something that they actually obey. So potential difference is written on the x-axis, current on the y, because this is potential difference is actually what we are controlling using a battery or a cell. So that's why it's on x-axis. It's an independent quantity, whereas current is what depends on potential difference. So that's why it's on the y-axis. Now they just talk about resistivity of a wire. You need to find its resistance. So they just talk about how you can basically calculate it. So area of a circle, that's basically the cross-sectional area that we talked about in the resistivity formula, and similar things like that. But nothing too major to go through. So if you understand all these equations, there's nothing new over here. So I'm just gonna move here. Let's see what they say. The gradient of the line of best fit is, yeah. So it basically proves this formula. So R equals rho L over A. So yeah, that's that. Let's just move forward from here. The IV characteristics. So IV characteristics is, that graph that we just saw between potential difference and the current. So that actually tells us the IV characteristics, current and potential difference characteristics of different materials. Obviously, it can be steeper, it can not be steeper, so it depends on the material again. So that actually is known as the IV characteristic. So the IV characteristic for a metallic conductor is a straight line because it's an ohmic conductor in most of the cases at constant temperature. They had to write this. The current through a metallic conductor, for example, wire or is directly proportional to the potential difference. So the current should be constant because you'll see in an example for the filament bulb, it is still a metal, but it's made in a way that its temperature increases as you increase the potential difference, and it's no longer uh, in that category. It's no longer behaves like an ohmic conductor. So we're going to find out. The fact that characteristics graph is a straight line through the origin tells you that resistance does not change. Again, we know that resistance would be fixed because it is fixed for ohmic conductors. Metallic conductors are ohmic. They have constant resistance provided their temperature does not change. So that's the main thing. The temperature should not change. The IV characteristic for a filament lamp is curved. So again, it's still a filament that is made up of a metal, and it should be an ohmic conductor, but it's made in such a way that the graph actually curves. If you keep on increasing the potential difference, the current no longer increases through it, so it becomes shallower, the graph becomes shallower, and the potential difference rises, but the current does not rise at the same pace anymore. The filament in a lamp is just coiled up length of metal wire, so you might think it should have the same characteristic graph as a metallic conductor, but it does not. However, current flowing through the lamp increases its temperature, so its resistance increases. So again, whenever we talked about the formula for the ohmic conductor, we said that it holds uh, unless the temperature changes. So as the temperature changes, it's a different story. It's no longer a straight line for the IV characteristic graph. So you have to keep that in mind. And the filament lamp is made in such a way that its temperature increases as you increase the potential difference. So it no longer behaves like an ohmic conductor. All right. The resistivity of a metal increases with temperature. So we already know as I told you, the resistivity of a material is constant as long as the temperature is constant. The resistance only depends on other factors like the length of the conductor, the cross-sectional area, but its resistivity value remains constant as long as the temperature remains constant. But here they say resistivity of metal increases with temperature. So temperature changes everything. So you should keep that in mind. So the formula for resistance rho L over A, obviously L and A do not change with the change in temperature. It's the resistivity that changes, and that changes the resistance as well. That's why you see that it becomes a bit shallower. And V is equal to IR, and R in that case is equal to V over I. So if this changes, it R changes with temperature. Obviously, if R increases, then voltage increases, but current does not increase at the same pace. So that's why it becomes a bit shallower. That gradient actually becomes a bit shallower because gradient is gradient in this case is I over V, because on Y it's I and on V. So it's basically R is the inverse of the gradient. So you see that the gradient here uh, decreases, which means that the resistance should increase. Does that make sense? I hope it does. So, all right. If anything does not make sense, just let me know. The resistivity of a metal increases as temperature. So we already established that. Semiconductors are used in sensors. So semiconductors are something that are forward biased, which means that current can only flow through them in one direction and not the other, because the resistance in the other direction is very high. We don't need to know how they work. We should just know that we don't need to know the principle behind them. We just need to know what actually happens. So semiconductors have a higher resistivity than metals because there are few charge carriers available. So that's the first thing. However, if energy is supplied to some of the semiconductor by increasing temperature, more charge carriers are released, so their resistivity decreases. This means that they make excellent sensors for detecting changes in the environment. You need to know three. Okay, thermistors, LDRs, and diodes. All of them are semiconductors. Let's see. So we talk about thermistor first. So the resistor of a thermistor depends on temperature. When the temperature, so obviously there are different types of thermistors. There could be some that you increase the temperature and resistivity decreases, and there could be some when you increase the temperature, the resistivity increases. But we are only going to consider that are NTC thermistors. NTC means negative temperature coefficient. What does that mean? It means that when you increase the temperature, their resistivity decreases. So temperature has an inverse relation for them. And throughout the, do you have any question?
Yeah, does the resistivity change or does the resistance change?
Uh, Resistance, how does resistance change? If the formula is rho L over A, there must be something that is changing the resistance on the other side. If you see that formula, so R is equal to rho L over A. There must be something that changes on the right side that makes a change on the left side. So if L and A are not changing, because physically it's the same thing if you change the temperature. So it's basically the resistivity that changes. So when resistivity of that thing changes with temperature, the resistance changes as well. So both of these things change for this equation to hold, right? So that's the reason actually. That
Yes.
answer your question. Yeah. So
Yeah.
resistivity does change. Yes, it changes. That's the only thing that changes in that equation. That then changes the resistance, because resistance actually depends on resistivity. All right. And we are going to consider only NTC, which is the negative temperature coefficient, which means inverse relation between resistance and temperature, which also means inverse relation between resistivity and temperature, because resistivity is directly proportional to resistance. So if you see the graph, it says what I said in words. So the temperature, when the temperature increases, the resistance is decreasing, because these are NTC thermistors, negative temperature coefficient thermistor. There are some that have positive temperature coefficient. We're not going to discuss that. But for them, when you increase the temperature, the resistance also increases. So it's a positive temperature coefficient, which means they have direct relation. Is there any other question?
Is it always curved and does it have to touch the y-axis?
Uh, it has to touch the y-axis. No, so yeah, it's touching the y-axis because temperature is something that is independent. You can control it. So obviously, if you go towards the negative temperature, you will see that the resistance for NTC would keep on increasing. So that's why it is touching the y-axis. You can make it on the other side as well, because obviously you can control the temperature. You can make it go towards the negative value like -10, -20, -30. But for NTCs, the resistance will keep on increasing as you go towards the negative temperature. Does that answer your question?
Yeah.
Yeah, and the relation where I've always seen it, it's always a curve. So you won't see a straight line which shows the relation between resistance and temperature. It's always a curve. Obviously, we don't know what's the equation behind resistance and temperature because it's not part of your curriculum. But whatever the equation is, there is a quadratic relation between them. That is why. So that is why you see that there is a curve here. So basically, one of these things is being squared on the other side, and the other thing. So it's basically a quadratic equation, whatever the equation that governs this change. But we don't need to discuss that. It's not part of your uh, course. It's just that you know that what relation is for the NTC thermistors. What is the relation with temperature and resistance? So you should know that a negative temperature coefficient. It tells you negative word is in the statement, so it tells you that there is an inverse relation between the two. All right. Similarly, and it makes more sense in this way, right? If you increase the temperature, which means that you are actually giving energy to the electrons or the charge carriers. If you give them energy, they will have more motion. If they have more energy, they have more motion. They'll move more. If they can move more, obviously the resistance which is holding them not to move is less. So that's why they move more. So it kind of makes sense. The positive temperature coefficients, how do they make sense? What is the chemistry behind it? We don't need to know that in this course. That's fine. LDR, the light dependent resistors. they work in the same way, so you understand that as well. They have a negative relation with light. So obviously when you shine light on something, you are again increasing the energy for that, which means that more flow of charges, which means that less resistance would be in play. That's why there's more motion, right? So that's why the relation is kind of similar in this case as well, with the thermistor, the NTC thermistor. All right. And again, it's a curve which tells me that there must be a quadratic equation in play behind the scenes. So that's why you have like a curve and not a straight line. So that's that. And as I told you about the diodes, the IV characteristic graph for them would kind of look like this. So if you see, if you go towards the negative x-axis, that means the current starts to flow in the other direction. The resistance is too high for any current to flow, right? You keep on increasing the potential difference in the other direction, which means you reverse the flow of current. You try to reverse the flow of current, and there is a lot of resistance in that case. You still see at the end that there is some current that flows through it, but obviously the resistance is too high, so you would need to provide a lot of potential difference for current to flow in the other direction, which we don't want to do anyway. We have to put like LEDs, for example. If you try to connect an LED with a battery or a cell, you they always have the. Have you seen any LED? Do you have like it in labs and you try to do some experiments using that?
Yeah,
Yeah, so they have like so they have two feet. One is a bit bigger than the other. That is
yeah,
to distinguish between the uh, positive side of that LED, positive leg of LED, and then the shorter one is the negative side of the LED, which tells you how you need to connect it for it to like light up. Because again, it's a diode. LED is a diode. It's in the name. LED is light emitting diode, so it has the same kind of IV characteristic graph. So current can only flow in one direction. It can flow in the other if you increase the potential difference by a lot, but you don't need to do that. It can also increase the temperature of it, and I don't know if maybe it will just blow up on your face. So you should not do that. That's why they have one of the leg longer than the other one. You can always cut it. It's just for you to distinguish which one is the positive leg and which one is the negative. It's not that it's required, just for you to know, because they can't write on that wire anyway. So that is for the user to distinguish between the two and how to connect it. So diodes only let current flow in one direction. So forward bias is the direction we want to go, which means positive potential difference flow through it. So forward bias is the direction in which the current is allowed to flow. That is the direction in which you give it some potential difference, the current is allowed to flow. The other direction, as you see, that's the negative bias, or sorry, the reverse bias. So in that direction, you have to provide a lot of potential difference for some current to flow, but it's not like the application of the diode. So you always give them current in one of potential difference in the other direction, which is the forward bias. So forward bias is the direction in which the current is allowed to flow. It's the direction the triangle points in the circuit, symbols on the right. So yeah, so this is how you draw it in the circuit diagram as well. Which so the arrowhead, it's kind of an arrowhead, the triangle. So it tells you which direction the current should flow. You can't connect it in the other direction. No current will flow through it. You have to provide a very high potential difference for the current to flow through it, and it's basically not the application it is designed for. So forward bias is the direction in which the current is allowed to flow. It's the direction the triangle points in the circuit, symbols on the right. Most diodes require a threshold voltage. So if you see here at the start, even if you have it connected in the forward bias, uh, it does not it still does not flow, right? So you have to provide it with a threshold potential difference for the current to start flow. If you have an LED and it has to work with usually that does not happen. So when I work with LEDs, I always have like 15 volt, for example, that like my power supply is 15 volts mostly in most of the cases. So in order to decrease, because most of the LEDs, they are designed to work around 5 volt. So what I do is if I just connect it directly to the 15 volt, it will just blow up after some time, because a lot of current will flow through it, which it is not designed for. So I have to connect a resistance in series in order to have less potential difference for the LED. So you have to always play with things. Maybe you don't have a power supply when you are working with them that has exactly the potential difference that you have. So now in that case, you have to use some resistors to help you, because in uh, series circuit, when you connect some loads, the potential difference, it splits. So it depends on how it splits based on what is the different resistance for different things. So that's that. Most diodes require threshold voltage of zero point 0.6 volts. So it's basically most of them. So obviously not all. Everything is different, but most of them have zero point 0.6 volts, which is, if you provide more than zero point 0.6, then some current will flow through it. Zero point 0.6 is the threshold voltage for it. No current flows when it is zero point 0.6, because it has enough resistance that does not let anything flow through it. So they're made in such a way. All right, that's that. Then we move to energy and power. That is something that we normally, in the household, we are mostly concerned about, which is energy, how much energy we are consuming. So what are the basic fundamental equations that actually work with them? So this is the basic formula that you should know. Power is equal to potential difference times current. I'm just gonna write it here just so that we know all the equations. So my pen. P equals IV. So if you know this relation, they're going to show you more equations, but you just need to play with this equation and this equation. If you play with these two, you can make multiple equations based on that. So don't need to like remember any of them. If you know this one, you can make all of these that are written here. So doesn't matter. I'm not going to write it. Other thing you should know is, what is power? Power is work done per unit time. That's the basic definition of power. So I'm not going to write that. You already know power is work done per unit time, or energy consumed per unit time, anything like that. So joules over time is what is power. Power is made in watts. Watt 1 watt is equal to 1 joule per second. So that's that. Gonna move forward. Nothing more to see here. Electrical energy, power. Energy is easy to calculate if you know the power. So if you know the power, it becomes a bit easier to calculate the energy. So obviously, if you know the power, the thing on the other side is work over time. So work done is something that is energy basically. So if you know the power, you know how long this power was flowing through. You can easily calculate the work done. So the formula that they have written here is work is equal to V times I times T. It's basically, again, just let me write the basic equation here, which is so basic I did not write it first. So power is equal to work done per unit time. And the other equation, did I forgot? No, I have written that. So if you see this equation, V is equal to W over Q. So using this equation and this equation, using these equations, you can come up to this one. Work is equal to VIT, because work done is equal, V is equal to W over Q. You can take Q on the other side, or no. So I think the way to go for this is P equals IV. So you replace V by W over Q. And when you do that so I can write it for you. It's fine. So P equals IV. You can replace V, or maybe if you have to reach this equation, it would be better to talk about it in terms of work done per unit time. So let me just, yeah, 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 yeah. So P is equal to IV, and P is also equal to work done over unit time. So I'm just going to write W over T equals IV, and you can easily, what's here? So it's WIVIT. So you just take T on the other side, and it becomes VIT. So you don't need to. remember any of these? We From all of these, it's just basic. You can reach this, so it's fine. We don't need to spend much time on that. And obviously, V equals IR, so you can play with the value of V or I using that formula, and you can deduce these formulas as well. So they are all pretty much related. As long as you know all the formulas on the left, you can easily make up all the other formulas. That's fine. So yeah, that's that. Let's just continue. So coming to the domestic energy, because we are more interested in the practical applications of that. So in the household energy, we don't use joules. We usually use kilowatt hour as the unit for energy instead of joules or kilojoules or megajoules or any of that. We use kilowatt hour. So work done is equal to, why we use kilowatt hour? Because work done, power is equal to work done over time, which means work done is equal to power times time. And power is measured in kilowatts because watt is a smaller unit, and in household we use more than that because uh, refrigerator uses I think it's rated at 300 400 watt. If you use an electric heater, it's around 1000 watts or 1000 to 2000 watts, the small one. So a better unit would be kilowatt to use for the sake of not having a very big number when we are talking about domestic energy. So for power it's kilowatt, for time it's hours in that case, because we're not going to use anything in seconds. We are going to use it for 30 minutes. For even if you charge a phone, it can take up to an hour or more than that. So we use kilowatt, and for time we use hour. That's why we reduce this unit for work done, which is kilowatt hour, because it is more practical. And they have just shown you what a kilowatt hour is equal to. You can always calculate this if you know the formulas, how 1 kilowatt is equal to 3.6 million joules. If you convert all of them, you can easily calculate it. So maybe no, don't remember that. You don't need to do that. Up to you. All right. And if you have to calculate the cost, that's why they always tell you the cost in terms of number of units you have used, because 1 kilowatt hour is one unit. That's how we use it, because a layman does not need to know that what is a unit. They don't need to know about kilowatt hour. So we say one unit means 1 kilowatt hour. So cost is always given in terms of unit price. So 1 kilowatt hour or one unit costs this much. That's how the energy companies give you the rate for that. And if you have to calculate the cost, you just simply multiply that price per unit with the number of units you have consumed. So that just gives you the cost, right? So pretty straightforward. It's about to save energy, blah blah blah. So it's just theory that they have burning the fossil fuels. This is the issues that I can just simply read it quickly. There's nothing rocket science going on here. Burning fossil fuels releases carbon dioxide into the atmosphere, which adds to the greenhouse effect and contribute to global warming. Sulfur dioxide released by burning oil and coal can also cause acid rain. Nuclear power stations produce radioactive waste, which can be dangerous to the environment and human health if it isn't disposed of safely. Even renewable energy sources like biofuels have an impact because of land is needed to produce them, because they require a lot of land. That is the basic issue with the renewable energy. They require a lot of space for them to run, and that's why still countries they are opting for other means of producing energy, because not every country has enough land, right? So they want to use it in some real estate and stuff like that. So they don't want to waste it for other things, and because just because of that reason, they are not completely shifting to renewable energy. All right. So that's that. EMF and internal resistance. So EMF is the same thing as potential difference. We'll find out what is the difference and why do we have to write EMF instead of potential difference. First is to be able to better understand is you should know all the batteries and all the cells. They have more capability, just like a car. I don't know if you're interested in cars, but when we talk about how much energy a car engines produce, we talk about it in horsepower. So we talk about different kinds of horsepower, like one is bhp, and the other one we talked about is, which is the more practical one if you ask me, is the wheel horsepower. So why is there a difference? Because engine, it produces the brake horsepower, which is bhp. uh, but obviously that is not what you end up with in the wheels, because there are a lot of things that cause a loss, and all of that horsepower does not, all of the bhp does not make it through the to the wheels. So the other one is called whp, and which is the wheel horsepower, and it is always less than what the engine produces. Similar is the case with EMF. So EMF is something that the battery has the potential to produce. That's the maximum the battery produces. But there are some internal resistances as well in the battery. So if you have like a, if we did not know about EMF, let's say we don't know about EMF, we just know about potential difference. So when you have a potential difference and you connect two loads to it in series, and you say one of them is just useless, we're not going to use it, the other one is the useful one, like you have connected a resistor in somewhere, and then you connect a bulb to it or a lamp to it. So obviously the lamp is the useful one, but obviously if the battery is producing 5 volts, the lamp is not going to get 5 volt, because if you have multiple loads in connected in series with a battery or a cell, uh, the potential difference splits, right? So sim- it's the same case. So in that case, the lamp is not getting all of the potential difference. It's the same case with the battery. So a battery can produce, let's say, 6 volts, right? But as the potential goes to the terminals from where you actually get the output, you are not getting all 6 volts from there. You may be getting 5 volts. That's why batteries, it's written on battery, it's a 5-volt battery. But it's not producing, it's actually not producing 5 volt. It may be producing more than that. But obviously there are some processes in the battery and there's some loss. When it ends up to the terminal, you don't get a 6 volt coming out of it. You get something else, you get something less than that. So we can assume that there's just a small resistance that is connected inside. If you add up all the losses inside and you just assume that there's just one resistor connected inside, that is actually causing, taking some of it, because it is connected in series with all the other loads, that is actually taking up some of the potential difference. So that resistance is called the internal resistance, because you can't do anything about it. You can make the battery as efficient as possible, but you can never make it 100% efficient. There is always some kind of internal resistance that is there, and we call it internal resistance. Does that make sense?
Yeah.
Yeah. So normally, when we draw a battery, we just draw these four lines, two bigger ones and two smaller ones, and that's it. We say that this much is the potential difference that is coming out. But if they have to show you what is underlying it, underlying a battery, they draw those and they draw a resistance inside that box, which tells you this much is the internal resistance. You can't do anything about it. You are not gonna get what 6 volt this is producing. What you're gonna get for this load is 5 volt, not more than that, because this is how batteries work. Can't make anything 100% efficient. So we can show that internal resistance, which is also called internal resistance, with a small letter R. Now that is called internal resistance. But what is the maximum that it is producing? Just like brake horsepower for a car, bhp. So we call this EMF. So you can say that in terms of a car engine, uh, this is the bhp. EMF is just the bhp that it has the potential to produce. But what you end up with is actually the wheel horsepower, which in this case is the potential difference that you're getting after that. So EMF is the maximum that it can produce, and obviously you can't have it, but it's denoted by EMF, end up with a small epsilon, I think it's called the symbol. So it's represent, obviously all the formulas you use are the same again, because there's no difference, still a potential difference. But it basically, small e represents that it's it's the maximum that the battery can produce, and you can use the same equations for that. Obviously you're not going to end up using all of that when it comes out. So let's see if they have anything that I've missed. So EMF stands for electromotive force, that you should know. Total amount of work the battery does on each coulomb of charge is called its electromotive force. So that's what battery does, but obviously it does not end up all of it. You don't end up with all of it when you connect a load with it. So that's the potential difference. Be careful, EMF isn't actually a force. Yeah, we already know it's a potential difference, not a force, but it's just in the name. And obviously, if it's a potential difference, basically it's measured in volts, right? So the same values, same formulas apply to that as well. Now, how we use it practically, what kind of questions we are going to get for it, you'll know shortly when we arrive to the questions. Energy per coulomb. So what's that? Energy per coulomb is work done per unit charge. So basically, potential difference they are talking about. Energy per coulomb supplied by the source, that's the battery. Energy per coulomb used in load resistance. So some of it will be used. So this is basically EMF on this side because that's the maximum the battery is producing. Uh, Energy per coulomb used in load resistance. So this is what the internal resistance is using. Some of it would be used by that. So this is basically used by the internal resistance. And this is what you end up with. Energy per coulomb wasted. Oh, sorry. I went through the. So sorry. So energy per coulomb wasted. This is what is consumed inside the battery. And this is what you end up with for the load. Energy per coulomb used in load resistance. All right. So that's that. And to show it in terms of equation, as I said, EMF is equal to capital V plus small v. Small v is for the small r. So this is what is loss inside the battery. And the capital V is what you get outside the battery. So this is what is written on the batteries. It's a 5-volt battery, which means you end up with 5-volt. If you go and buy a cell or a battery from a shop, it's basically what's written on it is not the EMF, because why would they write an EMF? It does not make sense. You don't actually get that. You actually get this capital V, which is eventually after it passes through the internal resistances, all of them. This is what you get. And they have simply used the formula V equals IR for them, and they have deduced other forms of it. So don't need to know that. So I'm just going to write this formula as you should know and understand this. So EMF is equal to the potential difference that you get outside, which is what we are interested in, plus a small v, which was the loss that was for due to the internal resistances. All right. So that is the formula that you should know. And obviously, if you have multiple cells connected in series, the EMFs for that will add up. And if they are connected in parallel, you know what happens with loads and potential differences connected in parallel. They just remain the same for all of those channels is what is written here. All right. So yeah. EMF calculation questions. We'll just go through the questions later. As long as we understand the theory, we'll just go through them in the coming days. Investigate internal resistance and EMF. We have already talked about these questions. I'm just going to skip it for now. There's nothing as important here. Now, coming to Kirchhoff's laws. So there are two Kirchhoff's laws. First one is because we are talking about conservation of charge and energy now. So Kirchhoff laws come into play here. So first Kirchhoff law is current entering a junction is equal to current leaving it. So if you have a junction as shown here, this is a junction. There are three ways that are coming from it, but there's only one inlet to it and two outlets. So we know all of the charge that is coming from this inlet uh, would be equal to sum of all the charges that are going out. Similarly, if you have multiple inlets to that junction, if you add them all up, you'll see that the charge that is coming out of that will be equal to that. So there's no loss of charge. Electrons cannot completely like disappear or anything. So that's Kirchhoff's first law. Then Kirchhoff's second law is about energy. And when we talk about energy in electricity, we always talk about potential difference, EMF. So, because what is potential difference? It is work done per unit charge. So, we're just talking about work done again, but in terms of potential difference, which tells us that we are talking about it in unit charge basis, actually. It's still energy in that regards. The total EMF around a series circuit is equal to the sum of potential difference across each component. So basically, it says whatever potential difference was provided by, or whatever EMF is provided by the battery, it doesn't get lost anywhere. All the loads are taking it. So if you connect 5 volt, if If the battery provides 6 volt EMF, let's say 1 volt was consumed by the internal resistance, then if you have two loads connected, equal two same resistance value loads connected to it, uh, they will take 2.5 volt equally, and it's totally, energy is totally conserved, because we're talking about potential difference. It's the same as energy per unit charge basically. So total EMFs in a series circuit would be equal to sum of all the potential difference across each component. So that's Kirchhoff's second law. It talks about the conservation of energy, which means conservation of potential difference. Kirchhoff's first law talks about the conservation of charges, which means they're talking about in terms of current. Does that make sense? I'm assuming it
Yeah.
does. All right. Okay. You can apply Kirchhoff's law to different combinations of resistors. I think you would have slight idea about it, how when you connect loads or resistances in a series, what happens. So how, when you connect them in parallel, what happens. So if you connect in series, obviously there is no junction. So you know that whatever charge starts to move from the positive terminal, for example, and goes to the negative one, it would be the same that comes to the negative terminal. So there's no charge lost here. Kirchhoff's first law should completely hold in this case. Now the second one was the conservation of energy, which is the EMFs. So whatever is the EMF produced by the battery, in this case they have written E here, and there's no internal resistance shows, so you can just uh, understand that in this case we are assuming that there is no internal resistance. That's why they have written it as EMF instead of writing it as the output of that. So these are connected in series. You know that it splits up when you connect loads in series. So that's why they have written E is equal to V1 plus V2 plus V3. And you know V is equal to IR. You can write it in this form. IR total is equal to IR1 plus IR2 plus IR3. Obviously, in series, you know that the current remains the same. Same current flows through everything, because obviously, what is current? Current is the flow of charge, right? So the charge, just 1 second. Okay, never mind. Uh, yeah, that's fine. That's completely fine. Okay, coming back. Yeah, so obviously, it's if it's a series circuit, the charge has no place else to go. It's a physical thing. So obviously, whatever enters R3 in this case, same would go through R2, same would go through R1, because there's no other way for the charge to go. It's a physical thing. If you go through, if the doors are connected, like if you go into one room and there's another door, you go through that. There's no other way for you to go, right? So you will keep on going through all the doors. But in case of parallel circuits, obviously, when you reach this junction at the top, there are two ways for the current to go through, the charge to go. It's a physical thing, it can't go through both of them. So some of them will go through R1 and rest of that will keep on going from there. That's why they have written I is the total current that is provided by the battery. So I minus I1 is basically uh, what then moves from that junction towards that, because I1 is something that is entering the first one, right? Then from after the second junction, obviously I2 has gone through R2 now. So the remaining current, I, which is the total one, minus both the I1 and I2, is something that will go through R3, right? So current splits up. It's a physical thing, it has to split up. But the potential difference in this case remains the same. Whenever you connect loads in parallel, it remains the same. If all of them, if the battery is providing 5 volts, all of them are gonna get 5 volts. So so V is equal to, sorry, they have written it in terms of I. So using V equals IR, they have replaced they have basically replaced I by V over R, and written V over R total equals V over R1 plus V over R2 plus V over R3. And when you, because voltage is same for all of them, they're connected in parallel, you get this equation for resistance. Now, I think in GCSE, you did not have this equation, right? So in GCSE, they used to just say that uh, if the loads are connected in parallel, the equivalent resistance, like the sum of all the resistance of the circuit, it's equal to the small, it's not equal to, it's less than the least resistance that is there, right? That was what was taught in GCSE, but now you have the equation as well, right? Does that make sense?
Yeah.
Yeah, pretty straightforward, right? So nothing too much. Uh, then there are worked examples. We definitely go. I'm trying to aim for going through all of the past paper questions that are related to this. So just please bear with me. I have allotted 3 days to them. So because we have two more lessons this week, and I'm just going to see if we have done enough questions for electricity. If you want to go through more, we can have one more day the next week, and we just try to finish all of them. All right. So you don't need to worry about that. Potential divider. So first of all, the word says what it is. They are dividing the potential, right? So a battery provides some potential difference, and you are just dividing it further. If you have to divide potential difference, you should know that in parallel circuits you can't do that. It has the same potential difference everywhere, right? In parallel circuits. So whenever they say potential divider, you have to split the potential difference, and that means the things are connected in series in that case. So that is actually what happens, right? So what potential divider does is it gets fraction of an input voltage. So if you have, so this is another thing that you can use. If you have like a battery of 15 volt and you only require 5 volts for something to work, and you don't want to give it more than that, you can use a potential divider. How does that work? You can make your own as well if you have the required resistors. So what you do is you connect two loads to it, like two resistances to it, and you know that the potential difference would be split among them because they are connected in series, and you connect your output through the one that gives you the required potential difference for you, right? So that is what potential divider is. They have shown you this equation, which is V1 over V2 equals R1 over R2. The potential difference of the voltage sources is divided into ratio of resistance as an equation. So if you have 2 ohm resistor and 3 ohm, you would get 2 by 5 potential difference. Yeah. So uh, as the potential difference divides, the resistance also divides in a similar way. Like it's a ratio, same ratio. So V1 over V2 is equal to R1 over R2 tells me that because V equals IR. So from V equals IR, we know that potential difference and resistance have uh, like a direct relation between them. So that's why if the resistor one has more resistance through it, it will get more chunk of that total potential difference that is provided by the battery. If the other one is less, has less resistance, it will get less potential difference that is flown across it. So this is that formula. I can write that one down for you as well. Mm, Not 100% sure if we're going to need this one. We can always deduce this one from others as well, but still, just to for the sake of completeness, I'm just going to write V1 over R1 equals, sorry, I've written it incorrectly. The ratio between the potential difference remains equal to the ratio between the resistances. All right. So that's that. And you can always use those formulas and come up with this one as well. I'm just going to write this one as well. You can always deduce this one from the equations that we have talked about as well. But if you have this in formula sheet, or if you remember this, you can always use it directly as well. So, but you understand the concept of potential divider, right? Assuming you understand. All right.
I don't know how it like, how does it split the current? Does it split the current, or is it the same current? The same current through the entire
Yeah,
circuit.
the same current goes through the entire thing. Uh,
Just the potential difference
it's
changes.
the yeah. That's the basic thing we know is whenever two loads or more than two loads are connected in series, the potential difference splits, and it splits based on the resistance. If you have a 3 ohm resistance and a five ohm resistance, you know that if you have provided 10 volts, more of that chunk will go to the 5 ohm resistor and less of that. It depends on the same ratio as I've written here, V1 over. V1 over V2 is equal to R1 over R2. So the higher resistor will get more of the potential difference, the lower resistor will get lower, and the ratio remains. There is a relation between the ratios. V1 over V2 is equal to R1 over R2. I think that is the most that you need to know. Um, I'm just thinking if uh, you should know this formula as well, but the thing is that we can always deduce this formula from other equations as well. Now, for now, we are just going to consider that we need to know this formula. So V out is what you're getting from one of the resistors. You have connected the resistors in such a way that this is what you require at the end for your appliance to run. This is the voltage that you require. So if you require higher voltage, like if you have 10-volt resistor connected, sorry, the 10 volt supply connected, which gives you potential difference of 10 volt, and you require, let's say, 7 volts and not 10. You connect two resistors, and the higher one is the one for which or across which you will connect your appliance, because obviously from the 10 you require more of that chunk, right? So again, for that you need to go back to this equation. V1 over V2 is equal to R1 over R2. So you have to see if you are still getting the enough potential difference that you need, or you need to change the ratio of these resistors. So for that, I'll come to the potential divider, which has the variable resistor connected. So you can play with the resistance. You don't need to always change the resistors. You can play with the resistance to have the required potential difference coming out of it. So just for now, just know that this is the formula that holds. We can always try to derive this, but I don't think we need to. So you just should just know that this is the formula. So this is the potential difference that you give. This is the what you get out of it. So you have to play with these resistances. If you know the potential difference that you're coming with, and you need to play with this to get the required, let's say you have 10 volt as an input, you require 8 volts. So you just plug in those values and then play with R and R to see what kind of ratios you can have and what are the available resistors, and you can make up your own circuit and get that output. Is there anything that you think still you don't understand?
No, it's fine.
Oh, all right. Hmm. And for light temperature sensor, all right, it's fine. Let's just go to the potential divider. So here they have shown kind of an application for like a light dependent resistor. Obviously, a light dependent, its symbol is like this, as we can see. Yeah. So yeah, obviously its value of resistance will change, which will change the resistance here in this formula, and which will change what kind of output you are getting here. So this will be the output that you're getting. So because everything depends on the resistance values, so for LDR, the value of resistance will keep on changing, and you can use kind of this circuit to work your, so you know the lights that auto shut down when there's light outside. So basically, they have some required potential difference for them to run. And when the resistance of the LDR, when there's light outside, the resistance of the LDR decreases. So you get more potential difference that goes as an output, because now the ratio changes between them, right? So you get more potential difference that comes across it, and the lamp starts to work. Um, yeah. Yeah, the lamp starts to work with different kinds of values. So this is a case of a thermistor that they have shown, and not an LDR, because LDR would be designed. So if you have to you have to make a system in which automatic lights turn on when it is dark. That has to be, I think, this output it should be connected to the other resistor and not this one, because when there is dark outside, the resistance across, no, sorry, it should be connected in the same one, the output, because when it is dark outside, okay, I'm confusing it. The output in case of an automatic light should be connected to the other resistor and not the LDR, because when it is dark outside, this resistance will be this is resistance will be higher. When this resistance is higher, there will be more potential difference across it. Sorry, I am again confusing it. There will be more potential difference that goes through this because the ratio now changes, and it will give more V output here when it's dark outside because there is more resistance to it, right? So then you will connect your lamp here and it will turn on when it gets the required potential difference. All right, so you can have different applications that you can use the LDR at, but it's always used in this kind of, it's a basic circuit that you use. And similarly, in the case of where you have to, when you have to control something based on the temperature, you use the same kind of circuit as well. So if this is a thermistor, and the obviously if it gets heated up, there is less resistance, it will the V output would be less as well. But when you have lower temperature, the resistance will be high and the ratio will change between these two resistors, and this will get more chunk of it because it has higher resistance. So it will get more potential difference and the thing will turn on if it requires, let's say, 6 volt. And as soon as it reaches 6 volt, you'll get the appliance would turn on. Does that make sense?
Yeah.
All right. The potential divider again. So potentiometer is depends on the potential. It's the same principle as you have for a general potential divider. Only instead of using two resistances, you use just one variable resistor, and one of the arm of the output is can be moved so that if it is connected here, this becomes it basically splits into two resistances, this part and that part. So now when you move this arm, you can change the value of R2 and R1, and by changing that you can calculate what kind of V output that you get because you're changing the ratio of the two resistances here. So you change the ratio of the two resistances, you change how V1 and V2 look like, and when you reach the amount of V output, which can be in case V2, so you change V2, you can run your any appliance using a potentiometer as long as it has the range of getting you that required potential difference. As long as it's you can't just connect like a thing that runs on let's say 220 volts and the battery can only provide 10 volts, so obviously that won't work. But yeah, that is how it is. So the only difference is that you have a variable resistor. All of these formulas hold for that. It's just that to change R2 and R1, you simply move this arm and it will change R2 and R1 for you. And obviously this V output is connected to how much it's connected to across R2. So whatever is the value here, you'll get that output from here as well. For just for the an application, they have shown how the loudspeaker and amplifier is connected here. You change the value of where the arm is connected to the variable resistor, and you change the ratio of those resistors, and then it makes you know what kind of V output you are going to get. And from that, uh, so basically, you can see what kind of V output you have and see if that is what you require. So nothing else that we need to go through from that. So I think this is all of the topics that are related to electricity. Other than that, I have written all the formulas here. So as long as you have the understanding of all of them, you can basically solve any question, and we'll find that out soon when we start to solve the questions from tomorrow. Thank you. Bye bye.